Okay. So when we talk about these are hydrocarbons, which means they are compounds that consist of predominantly two elements. What elements is that going to be if it's a hydrocarbon? Hydrogen and carbon. All right. And so there are three classes in general. We have those that are alkanes. Oops, it's supposed to be an E. And these are hydrocarbons that have single bonds. Right? So one example of that would be this, which is C4H10. Of course, you can draw all the carbons and the hydrogens out if you want to. That's an alkane. You're going to find out it's called butane. So that's an alkane. Alkanes are relatively boring. Then we could have it if it contains a double bond, or at least one double bond, I should say. I don't know why this is giving me fits today. So, for example, that's what that would look like. You're going to find out there are more nuances with that whenever we cover alkenes later on in this semester. Oh, I couldn't give it away. Those are alkenes. So if they have a double bond, they're called alkenes. And you'll find out that that one right there is specifically called trans-2-butene. Not that I actually expect you to be able to name it at this point. If we have alkanes, we have alkenes, single and double. It means we have to have something for triple bonds. And what are those called? Alkynes. And so if I'm sticking with the... Actually, this time I'm going to draw it out to make it really obvious and to not distort the three-dimensional structure. Because a lot of times I draw them whenever I'm in a hurry. I draw it just like I would the alkene above it, and I just put the three bonds in there. But then I have to be careful because people, if I say, what shape is that? And they'll give me bent or something. In reality, alkynes are linear. So that's why this time I don't want to distort your perception. But yeah, that's an alkyne. And we'll find out that that one's called 2-butene. 1, 2, 3, 4. Yeah, 2-butene. One thing you will have to just memorize, and those are the prefixes. And so we actually already do this when we talk about ethanol and methanol and methane and ethane, propane, butane, butene. And so I expect you to memorize up through 10. Oh, whoops, that is not the one I thought it was. That's not it either. Okay. All right, so I want you to memorize, and actually I think that it's probably not covered until a little bit later in this chapter, but it just makes sense right now since they talk about alkanes, alkenes, and alkynes, that you just go ahead and know your prefixes from 1 to 10. What's the prefix for something that's 1? I mean, in organic chemistry, it's meth. Like methane is an alkane that has 1 carbon. Okay? So that's meth. 2 is eth, like ethanol, which I drew here, has 2 carbons. Like I said, these are the prefixes. The third one, 3, is prop. It's like propane. So now you already know how to draw the structure for propane because that just means it's an alkane that has 3 carbons and they're all single bonds. That's why it's pretty simple. Actually, if you learn the rules, the correct rules for naming, you can draw it, or drawing and you can name it. It's not that difficult once you learn just the basic rules. That's why it uses a lot of oh, that's propane. It's pro. I forgot. I started using a specific example. That's pro. 4 is bute, because that's what I was talking about on those examples. So bute, B-U-T, like butane, like a butane lighter. 5, pent. Whoops. So honestly, usually the first 4 are the hardest. People mix them. For whatever reason, the ones that I see people mix up the most is prop and bute. So I'll talk about it in a moment. So 6 makes sense. It's hex, like a hexagon. 7, hept, which if you think back to geometry, it's the same. 8 makes sense. It's oct, like an octagon. I'd also say like October, because October is actually named after it. Does anyone know, little Jeopardy factoid, why, if October is literally means the 8th month, why is it really the 10th month? What months don't? Someone said August is one of them. July and August, and so back in the old decimal base, not decimal base, but the 10th one. That's why Oct, Nov, and Des, December means 8, 9, 10. But in reality, Julius and Augustus Caesar come along, so they named months after themselves, July and August, and so it breaks it up. Little side track there, but that's why Oct. Don't get it confused. Very few people do and think it's 10. Think of it based off the months. It's like an octagon. Okay, 9. It's not nov, but it's non or known, which is, I have had some people at least confuse it with November, but non or known, like nonane and nonane, being an alkane that has 9 carbons and are all single bonded. And then finally we have 10, which is dec, or yes, was dec. And so it's meth, eth, prop, but, pent, hex, het, octagon, and dec. Meth, eth, prop your butt, not but your prop. So that's way to make a little bit more sense. Other than, because I tell you, these are once all people confuse meth and eth. But by far, the mistakes I see the most in naming or drawing, vice versa, is mixing up 3 and 4. By far. Okay. And so that's why, for example, if I drew this, what would that one be? You should actually be able to name this one already. This is octane. 1, 2, 3, 4, 5, 6, 7, 8. It's an alkane, has 8 carbons, it's octane. So we're going to find out later on like what happens when things start to be added on and stuff like that. Okay. So there are some that have common names, like this is ethene. Okay, we say I don't have it, and ethine, but it has common names, ethylene, like ethylene glycol, and acetylene is an acetylene torch. But you can go back to their actual, it's called IUPAC, the IUPAC naming, which is ethane, ethene, and ethine. All right. The only thing I want to point out here before we actually move on, and there's a couple of terms that you get used, and that is aliphatic and aromatic. Okay? And the only thing that I want you to derive from this, these are all hydrocarbons. They're all going to be hydrophobic, means they're going to exclude water. Aliphatic versus aromatic. Aromatic are those, they are cyclical. And we're going to talk about that in greater detail, whereas aliphatic are not. Okay? And none of that, but aromatics are cyclical that have to have double bonds in them. Okay, they are called aromatics because originally the ones that were discovered or first discovered had smells to them, but they all don't have. First of all, they all don't have good smells, but they all don't have necessarily smells, and so it's kind of like a historical thing. But otherwise, if it's this carbon-carbon single bond, then they're usually called aliphatic hydrocarbons. All right, we actually already did all this. Okay, this is where it gets a little tricky. So remember, when we talk about electrons stuff, there's has particulate attributes to it and also has wave attributes. And the simplest way to imagine this is if you've got two nuclei coming together and they start to approach, and so we're first going to talk about two hydrogens, and how many electrons are in a hydrogen atom? 1. How many protons are in it? 1. So this is this one, here's another one. Of course, naturally occurring hydrogen, you find this hydrogen gas is ch2. What happens is as they start to come together, if they're too far apart, there's no bonding. If they get too close together, it's going to be bad because both the electrons are going to be, the two electrons are going to be repelled from each other, and so will the two nuclei that are positively charged. So there's, it's sort of like Goldilocks, that whole idea that there's something that's just right. There's that perfect bonding angle between not angle, but the perfect bonding distance. And since it's a wave, if you think back to physics, you can either add them or you can subtract them. And so that's why we're going to get this whole idea that there is a bonding orbital, and then if you subtract it, it's called an anti-bonding orbital. And if they're not bonding at all, it's called non-bonding. Okay. And we're talking about covalent bonds here. That's all that I want to talk about. This is where, the term is quantum mechanics. It gets kind of scary when you think of it about that way, but that's why I usually just like to talk about it using more simple mechanics than that. All right, so this is the whole idea of what I was trying to do with my hands. We have the two hydrogens. As they come together, the orbitals start to overlap, and there's this optimal distance whenever the electron from, right here in this example, the electron from my right hand is just close enough to the proton in my left hand to be attracted to it, but not so close that the two protons are antagonistic or the two electrons. Okay, so there's that ideal thing. And if, once again, this is just showing that you turn it at 90 degrees, you would only see, it would appear right now that there'd just be one proton, or you can imagine you have a gun, you turn it one direction, you see the body of the gun, you turn it the other direction, you're looking down the barrel of the gun. Please do not look down the barrel of a gun, but that's the same principle right there. My little litigious disclaimer. This is just showing this whole idea with like color coding and how the term here is valence bond theory, because then the valence electrons overlap just right, and you get that nice pretty color and all that kind of stuff. But all right. So that was valence bond theory. And then there's one that's molecular orbital theory, which for hydrogen it's really, really simple because there's only one possible. There's only one electron and one electron. So then this is this whole idea that you can have two possibilities. Well, I guess in theory 3, but you don't have 2 electrons. You'll see in just a moment what I mean. Okay. Hopefully you'll see in just a moment what I mean. So we have one proton. I'm going to try to keep these. So this is hydrogen over here with its one proton. And then I have a hydrogen over here. I said proton, but it's with its one proton and its one electron. Okay. These are the energy levels. So we have an energy level there for it. And that's where its electron is residing. And likewise, we have this one way over here with its one electron residing. So in theory, what we could do is as they start to approach each other, we're going to get this overlap. And instead of just having the valence, which I know for hydrogen, the valence electron is the same thing as its orbital for the whole molecule, but whenever you get to ones that are more complex, it's not. So for example, methane, CH4. But as they start to approach each other, you're going to get a couple different possibilities. Whoops, that's supposed to be a straight line. I did not do a very good job with it. Let me try again. That's a little bit better. Okay, so what happens here is you could have this electron Okay, so I'm trying to go down. Which one of these are all energy levels, but which one of them is more stable, makes sense, based off of what you know? The one on the bottom, and that's molecular orbital theory. That's the bonding orbital for the molecule. And then the problem is if you try to force electrons together into, and you can, this is an energy diagram, so if you add enough energy, you can force the two electrons in there together that do not want to be. That top energy level right there, that top scenario, is called the anti-bonding orbital. That the bottom one's bonding, that one's anti-bonding, and if there was one in the middle, it'd be called non-bonding. And when we see some of the higher level molecules later on, not in this chapter, I don't really think they go into it, but later on when we talk about aromaticity and anti-aromaticity, you actually do have sometimes ones that get into the non-bonding. This is where they're just not involved at all. Okay. It is a simplification of what versus what they say, but at least for me, it's a little easier to follow along looking at it that way. So they talk about what if you were subtracting versus you're adding, and then blah, blah, blah. But okay. So here's little pictures of the possibilities. So they do it here if it's the bonding, this is lower energy, see they come together. If you subtract the two, then you actually create this, it's called a node, because that's the possibility of no bonding occurring, not a real bond occurring there. They're going to be repelling from each other. All right, so here's actually what I was drawing before. Oops, yeah. All right, so but what happens once we talk about, that's fine for hydrogen, but let's look at methane, which is CH4. It doesn't really explain too much with methane, and so I actually don't like the way we do it. I know it's a big surprise. So this is the way, and I actually used to have a little devotion of sorts that I would try to use to explain the bonding of methane, but it takes a little bit longer than what we have time today. Where carbon was Christian, H was the hydrogen was the heathens. So I had to kind of push it, but organic chemistry doesn't lend itself a lot to that. At least in biochemistry, I get a lot of references to like Moses in the Holy Land. The fact that, for example, pyruvate can see the citric acid cycle but can't enter in, just like Moses in the Holy Land. So, but that's just, yeah. If something can see the mitochondria but can't enter in, that's Moses in the Holy Land. You get Moses in the Holy Land alive. I ride that horse. So, okay. So this is the problem, or a potential problem. We have a carbon. How many electrons does the carbon have when it's coming into the relationship? How many electrons is it bringing into the methane? How many valence electrons does it have? 4. And so we have 1, 2, 3, 4. And for hydrogen, first of all, methane would have how many hydrogens total? 4. And each one would have 1. I'm only going to draw one of them right here for clarity's sake. Okay. All right. So let's just do a little thought process here. I forgot. I know that there's a specific term for it where you're just supposed to imagine like what would happen. We're going to draw the energy diagram for just carbon. Okay. So for that carbon in that color, just the valence electrons, because those two interior ones, they don't do any bonding because they're on the interior. So we're only talking about the valence electrons. So this is from the 2, the energy level is equal to 2, n equals 2. And so those first 2 electrons, what energy level are they in? Think back. 2s, okay? So where it's down here. 1, 2. And then we have 3 p's. And technically it'd be px, py, and pz. But I'm just going to put p's up there. And so where are the other 2 electrons? The first and the second. Px and py. So that's fine. We actually have how many, if this was a hotel that we were running, how many beds would be left total? How many beds? Nine. 4. We have 4 spots that we can fill in, right? We can have 1 on the px, 1 on the py, and 2 on the pz, or pz for English speakers. So the American English speakers. So for that, you don't want to write this down. necessarily, because it's wrong. Okay, that's why. But I'm saying this. Just imagine what this means. We could have hydrogen 1 here, hydrogen 2, hydrogen 3, and hydrogen 4. And see, everything is perfectly fine and dandy. You would think. Okay. But what's the problem with this? What's one potential problem that we have? Two hydrogens are they're like the little. No, I'm trying to be politically correct, and I can't think of one. So I don't know. I know. Yeah, they're like the two little kids like wandering off. You know, if you're trying to do like a field. I can't think of anything politically correct, so maybe I shouldn't go there. All right. Okay, so they can be off by themselves, like in some corner. I mean, they're not even a part of the molecule. Okay, and so we have two of the hydrogens hanging out with the carbon. We have two of the electrons from the carbon just keeping back, and then we have two hydrogens kind of wandering around out there someplace. Okay, and so that means that it can't happen, and that is not the way. Plus, even if we somehow, I can't even attempt, we actually already know what the structure of methane is. What's the physical structure of it? What's that structure called? Tetrahedral. And so remember, I'm just going to draw it over here to give you an idea, just remember what it looks like, to keep in mind. And all four bonds of those are equal in length. We already know that. However, here, that's not true. This bond, since it's stronger, would be shorter, and those three bonds would be longer because they're weaker. And like I said, and one of the bonds would be like sticking out their way out and not even part of the molecule, so it doesn't make sense. So what happens instead is this. Oh, whoops, it's going to take off my little tetrahedral. You can add just a little bit of energy. It doesn't take a lot. And I used to write down the exact number, and I didn't bring those notes, but I want to say it's like, I can't remember how many kilojoules. It's not that much. But you add just a little bit of energy, and you can take, and I'm not skipping any steps here. You can take one of these electrons here and pop it up into that energy orbital. Okay? It doesn't take a lot of energy, just enough to go from an S to a P. So whenever I redraw this, it's supposed to be 2. We now have something that looks like this. Now, once we don't do this part, we actually have 4 spots where one hydrogen will be interacting with one electron from carbon. But why is this also not right? Why do we know that it's not really this right here? 1, 2, 3, and 4. Well, it can't bind on the inner, and what about the shape? What shape would this be? They're also not going to be the same bond lengths, okay? I can't even attempt to draw this. One of them, remember the S kind of looks like a circle, so somehow we have a little circle on the inside, and we have dumbbells sticking all over the place. And so that doesn't really work, because this would be a short bond, and these would be 3 longer bonds. So we know that that's not right either. So give just a little bit more energy, that whenever it goes to bond, you can take that S and those 3 p orbitals and mix it together. Okay, instead of keeping the S separate and keeping the p's in one way, you mix them together, and it's called hybridization. It's orbital hybridization. All right, so now we actually have 4 orbitals that are the same energy. So they're degenerate, and this is a time when degenerate is good. Okay. And if you notice, I deliberately made them to where they're higher in energy than the S, but lower energy than the P. We have 1 carbon electron in each one. And then we can now put in our 4 hydrogens. And all is right with the world. Okay, so that's methane. We have 4 bonds. They're equal in length because they're going to be all equal in energy. There's going to be tetrahedral, which is, that's where we get this whole idea. And I don't remember if you remember it from, I don't remember if you remember it. How would I know that? I don't know if you remember it in Gen Chem, but these orbitals are called sp3 orbitals. Because it literally means you took one s and three p's and you mixed them together. So each one of those is called an sp3 orbital. And so that's where that comes from, that whole process there. Okay, so we only have like 3 or 4 minutes, and so what I want to show you is that explains methane, but what happens whenever, I want you to think about what happens whenever we do ethane, which is also called ethylene, because then it's, not ethane, I'm sorry, but a double bond, ethene. Oh, come on now. That's supposed to be 2 on that one hydrogen. Okay, so then, does anyone remember, you may already remember this off the top, what kind of orbital hybridization is in this kind of thing? So the sp3, it's, so we're going to find out, and I don't know if we'll take the time on Monday to do this or if I'll just do a video. I actually already have a video for alkynes, which is along the same line versus alkenes. That's available on the website, not on MyFire. So I'll either do this as a specific video tutorial or we'll cover it a little bit in class. I don't want us to fall behind. But what we're going to have to think about is what it means. And if you think back to, and let me just draw methane again. Remember, this was methane all the way out. And each of these, we've already talked about, is an sp3. I'm not going to write sp3 on every single one because for time and also for clarity. Remember, that's an sp3 orbital. It's tetrahedral. And what is the angle between it? 109.5. Sounds like an easy listening radio station. Okay, but does anybody remember what's the name of that kind of bond right here? It's a single bond, but it's also called a sigma bond. These are sigma bonds. Whereas whenever you do double bonds, you have a sigma bond and a pi bond. And so we're going to actually explain, like I said, either on class on Monday or on a video, explain that where does that pi come from? So how do you get that piece of the pie? And so to speak. All right, so how are we doing on, yeah. Because I'm afraid it's going to take a little bit too much time to give it, we would go over for me to give it the amount of time that I would like to give it to describe here. Okay, are there any questions over this so far?